In the first topic of this video, we're going to take a look at the big O notation. Now, a big O notation is a mathematical notation used to represent the efficiency of an algorithm. There are multiple purposes for the big O notation's existence. One is to, of course, describe the worst case scenario or the upper bound of an algorithm. Basically, it shows the time and space complexity of an algorithm in its worst case scenario. Now, as the input grows, we get a sense of idea of an algorithm as to how it functions and how slow or fast the algorithm is. To judge its efficiency, we are using the worst case scenario, or simply put, the big O notation. Now, we can use the big O notation to compare two different algorithms and their efficiencies. Now, why are we using the worst case scenario instead of the best case scenario? Now, worst case scenario is big O. Best case scenario is the big omega. And in between, which describes the worst case and the best case, is the big theta. Why are we not using big theta or the big omega? We're using big O, or the worst case scenario, because we can get a fair idea of the resource allocation. We can get to know, we can have a reliable estimate of how long an algorithm will take to run, even in the most unfavorable circumstances. Now, we also know that we can compare two different algorithms based on their worst case time complexities to determine which one is more efficient. Now, essentially, there are two ways to measure the efficiency of an algorithm, that is the time and space complexity. Now, time complexity will be discussed later, but to simply sum it up, it measures how the runtime of an algorithm increases with increase in its input size. Now, if I input more numbers into an algorithm, then the time complexity may or may not increase depending on the efficiency of the algorithm. Space complexity measures how memory usage of an algorithm increases with the input size. Now, essentially, if I input more numbers into an algorithm, then the space complexity might or might not increase. Both time and space complexities can be measured by the big O notation. This sample code shows that we can find a maximum value in an unsorted array. Now, the worst case scenario essentially for this code is O of n, because we have to iterate through every single element in an array. If the number of elements in an array is represented by n, then our worst case scenario, or the big O notation for this specific code, would be O of n. To explain this code, we have an array ARR, and we are initializing the first value of the array to max. Now, we're using a variable num to iterate through the array and find the maximum number. If the first num is greater than the second num, then replace the first num's value with the second num in the variable. Now, that is how we find the maximum number in an unsorted array. Essentially, we are iterating through each and every element in the array. Hence, the worst case scenario for this specific algorithm would be O of n. We have several time complexity or space complexity notations over here, wherein O of n and O of log n are fairly good. That is, their O of 1 and O of n are the best out of them. O of log n is really good. O of n log n is bad, and anything greater than n log n, that is O of n to the power 2 or 2 to the power n or n factorial, represents that the code is really not usable or the code is really slow. Further, to explain time and space complexities, my friends Janmajay, Garima, and Samara will help you out.
So, hello everyone. Today I will be presenting an introduction to the time complexity. Time complexity is a key concept in computer science that helps us to understand the efficiency of our algorithm, making it crucial for designing high performance applications. So, the first question: what is time complexity? Simply put, it's a way of measuring the time an algorithm takes to complete relative to its size of its input. For example, an algorithm that has to process a list of 10 items will usually take less time than that processes 1000 times. Time complexity helps us to identify these differences, which is crucial for building systems that need to perform well with the larger data. Now the next slide is types of time complexity. There are different type of time complexity that represent varying level of efficiency. So the first one is constant time. That means that the time taken doesn't change with its input size. Second, logarithmic time. It reduces the input by half each time, like in the binary search. Third, linear time. It scales directly with the input size. Fourth, quadratic time. It grows faster as the input increases, like in the nested loops. And lastly, we have exponential time, which grows extremely fast and is generally not feasible to larger inputs. Now, Big O notation. Big O notation is a standard way of expressing time complexity. It describes the upper limit or the worst case performance of an algorithm, which help us anticipate its behavior with the largest inputs. For example, if we take a sorting algorithm, often ranges from O n log n to O n square depending on the method used. Big O allows us to easily compare these algorithms and choose the most efficient one for our needs. Now, analyzing time complexity. To illustrate this, let's look at a basic example, looping through an array. Here we go through each element once. So the element time complexity is O(n) because the time taken increases linearly with the size of an array. This kind of example is common in search algorithms that require us to check each element. Now, different data structures have unique time complexity for operations. Array, for example, we have O1 access time since we can directly access any index, but searching through items take On. Linked lists, however, have On for access since each element is connected by pointers. Hash tables allows average O1 time for operations, while binary trees generally offer O log n for balanced trees. Choosing the right data structure is crucial for optimizing performance. Hence, we can say that time complexity is essential for evaluating and improving the efficiency of our algorithm. By analyzing, it can build scalable and performant systems. Thank you.
Hi everyone. Today we are diving into space complexity, a key concept in understanding the efficiency of algorithms. Space complexity measures how much memory an algorithm uses, which becomes especially important in environments with limited resources like mobile apps or embedded systems. Let's start with the basic ones. Space complexity can be broken down into two main parts: fixed and dynamic requirement. Fixed space is memory that doesn't depend on the input size, things like constants or the code itself. Dynamic space, on the other hand, depends on the input size and includes variables, dynamic data structures, and recursion stacks. This distinction is crucial because it helps us eliminate an algorithm's total memory needs more accurately. Now we'll talk about auxiliary space. This refers to extra memory that an algorithm needs beyond the input data, and when we add it to the memory required by the input, we get total space complexity. For example, some algorithms like merge sort use extra memory for temporary storage, whereas others like insertion sort don't require as much as auxiliary storage. To see, here it's like given here. Hmm. Now, to make sense of all this, we use big O notations in a way to quantify space complexity as a function of input size. Common space complexities include O of 1 for algorithms with constant space like simple loop, and O of n for those that require memory to store inputs such as array or linked list. Finally, to see some space complexity in action, think of recursive functions or sorting algorithms. Recursion stacks in algorithms like factorials or Fibonacci calculations can increase space needs dramatically, and sorting merge sort uses O of n space due to extra storage needs, while quick sorts auxiliary space is generally more efficient. In short, space complexity is an essential factor in writing efficient code, especially as applications scale. Thank you for listening. Thanks.
Today, I, Samira, will be discussing what is a good code. This is especially important for writing code that's not just correct but also efficient, scalable, and maintainable. Good code in DSA has several key qualities: efficiency, correctness, readability, scalability, modularity, edge case handling, and testing. Each of these elements contributes to creating solutions that are practical and sustainable. Let's dive into each quality and explore why they matter. First up is efficiency, which means optimizing both time and space complexity. We often use big O notation to measure this, as it describes how an algorithm performs as the input size grows. For example, consider sorting a list. Bubble sort has a time complexity of O(n square, which means it's very slow for large data sets. By contrast, merge sort is more efficient with a time complexity of O(n log n, making it much faster for larger data. Next, we have correctness, which is essential for code that does what it's supposed to do. A correct algorithm is one that works for all inputs, including edge cases. Let's take binary search as an example. Binary search finds an item in a sorted list by repeatedly dividing the search space in half, which gives it a time complexity of O log n. However, this only works correctly if the list is sorted and all midpoints are calculated properly. Now let's talk about readability. Code should be easy to understand for other developers and for future reference. This means using meaningful variable names, comments, and a clear structure. For example, a pathfinding function where variable names like visited and neighbor help make it clear what's happening. Imagine you are reading this code 6 months from now. Would you still understand it? That's the test of readability. Now, scalability. Scalability is about preparing code to handle larger datasets. For example, if we need to check for duplicates in a list, an array would require O(n) time for each lookup, but using a hash map, we can reduce this to O(1) time per lookup, which performs much better as the list size grows. Modularity. Modular code is broken into smaller single purpose functions. This not only makes code easier to read but also easier to test and reuse. In a graph transversal example, we separate the depth first search transversal into a helper function, DFS helper. This approach helps our code organized and allows us to easily adjust parts without rewriting the entire function. Next is handling edge cases. Handling edge cases is crucial to making code robust. Edge cases are unusual inputs like an empty list, very large numbers, or one element list. If we don't handle this, our code may fail unexpectedly. Last one is testing. Good code in DSA is thoroughly tested across a variety of scenarios. Typical cases, edge cases, and stress tests with large inputs help ensure that the code works reliably in different situations. Thank you.